Okay, so in the last video, we computed the cohomology of KZ2 and using the Sayre spectral sequence, and now we're going to push that computation further. So we'll take the fibration whose fiber is KZ2. Again, this is the path loop fibration. And our base will be KZ3. So our goal is to compute the cohomology of KZ3. And let's see, this is a fibration. And we learned last time that the cohomology of KZ2 is just Z adjoin Y, where Y is in degree 2. We also could have seen that because we said it was CP infinity. And then we want to use that and the cohomology of a point to bootstrap our way up to the cohomology of KZ3, again using the Sayre spectral sequence. So I want to use the, what am I trying to say? I'm trying to say that this is a free Z module, and so the E2 page is indeed the tensor product of algebras of the cohomology of KZ2. Maybe let's write KZ3 first, not that it matters, tensored with the cohomology of KZ2. And our spectral sequence should converge to the cohomology of a point, since the path space is contractible. We're also going to use the fact that this is not a map. I just want to make the note that this is now 2 connected. Okay, so that will all help us. And I think I'm going to need a lot of space here, so I tried to make a big grid. And remember that we'll have the cohomology of the fiber over here and the cohomology of the base over here, so that's the thing we're after. The cohomology of KZ3. And again, I'm going to draw the E2 page, though this time I will sort of think of multiple pages as being on top of each other. Okay, and we may have to do some sort of scrolling back and forth just because it's hard to fit this all on one page, so bear with me. All right, let's start with what we know, which is the cohomology of the fiber. So we put that over here in the first column, and we know we've got Z in even degrees, of course this continues. We even know it as a ring, so it was polynomial in this class y, so that's like 1 y squared, y cubed, y to the 4th, y to the 5th. I hope that you can read these. Okay, and then we've got zeros in between. And then we talked about how KZ3 is 2 connected, so I have zeros here, and that means I can fill this all in with zeros. So we immediately know the first 3 columns of our spectral sequence. And now we'll get to work. Okay, so the first step is to start to kill things off, because we know that we should be converging to the cohomology of a point. Sometimes I find it helpful to sort of draw that off in the corner, remind myself what I'm converging to. So everything needs to die except this first copy of the integers. Everything else is going to have to go. Okay, so in particular, this next copy of the integers needs to die. And again, thinking about differentials, nothing can come from the side over here. And we're already on the E2 page, so I don't even need to consider D1, though in this picture it looks like it would be 0. But we don't know what was there on the E1 page. On the E2 page, there's, whoa, jumping around on me. Okay, on the E2 page, there's a possible D2 differential. Oh, that would have to be 0. And then the only next possibility is a D3 differential. So if we want that copy of the integers to die, then we're going to need at least a copy of the integers there in degree 3. Okay, and this is generated by something. Let's just call it z to give it a name. So actually, let's call it z. Okay, sorry. Now remember that this E2 page is supposed to be the tensor product of the cohomology of the base and the cohomology of the fiber. So that's going to give me a z here that's generated by yz. Okay, that's just because I've got the same coefficients here again. Of course, here in at height 1, my coefficients are 0. So I actually know these are zeros all the way across. Okay, and then where were we? So then I jump up one, and the coefficients are z again, so I know that should be that z repeated. But I also know, because of this tensor product fact, that it should be generated by y times z. Okay, oh, and I forgot to draw in my D3 differential. So here, this is kind of a misnomer, right? Because I'm drawing the E2 page, but I'm noting that this D3 differential must have happened here. And so in a sense, I'm really drawing all of the pages at once and just trying to remember what lives onto the next page. But we saw already that D2 on this is 0. So this whole group, in a sense, lives again on the E3 page, and that's what supports the differential here. Okay, saying this a little bit out of order, so hopefully this is clear enough. So we had that D3 differential. Once we know that there's a class there we could call z, then we know from the tensor product we've got yz. Okay, and I can also start to compute these differentials. So maybe let me at least try to fit some of them here on the side. So we just said that d3 of y is equal to z. And we're going to use the Leibniz rule to say that d3 of yz is what? Well, it should be d3 of y times z, and then plus, because y is in degree 2, y times d3 of z. Okay, well, z is on that bottom edge, so it doesn't support a differential. So I really just have d3 of y times z, and so that's just going to give me z squared. Now, z squared could be 0. I don't really know. But if it isn't 0, then it's something that lives in degree 6 here. Okay, so how are we going to figure that out? Well, we'll have to hold off, so let's continue on. Let's think about d3 of y squared. Well, that should be d3 of y times y plus y times d3 of y, and that's just z times y plus y times z. Z is in an even degree, and remember that the cohomology is graded commutative, so we can swap the order of y and z as long as we do it at the cost of the minus sign, where we take the product of the degrees. Anytime you've got one of them has an even degree, it's going to commute, so that is 2yz. Okay, and in fact, we can play that game in general. d3 of y to the n, this is basically a derivation saying that we follow the Leibniz rule, so it should be n y to the n minus 1, and then times d3 of y, and you can check that by induction. Okay, so in this particular case, I guess that tells us that we get n y to the n minus 1 times z. Okay, so what does that tell me? That tells me that y squared is going to come hit 2 times yz. So let's write times 2 there. Again, this is a D3 differential, so that's really happening on the E3 page, but we now see that that's an injection, but it's not an isomorphism. Okay, great. What do we want to do next? So, yes, okay. So now that we have this injection, that means that everything here will die on the E3 page, right? It won't live to the E4 page because it's not in the kernel. But when we look at this spot, we see we have a copy of the integers, and then coming in is the times 2 map. So if this map is 0, then we'll have z mod 2 show up on the E3 page. And in fact, if this map is 0, it can't support a D2. It can only support a D3 because D4 would be out here past the first quadrant. So if that were to happen, then this would leave us with a Z2 in this spot, and we're supposed to be converging to the cohomology of a point. So everything but that first copy of Z needs to die. So there better not be a Z2 there. And that tells us that, maybe this is sort of for a different reason, so I'll use a different color. That tells us that there should be a Z mod 2 here to receive that differential. And that's again going to be a D3. And that Z mod 2, we actually already know that it should be generated by Z squared, because we know that D3 of YZ is supposed to hit Z squared. So it turns out Z squared is not 0. Now graded commutativity tells us something in an odd degree it should square to be 0 if it's generating a copy of the integer, say. But if we're generating a copy of Z mod 2, then we're fine. Okay, so we've now taken care of this spot because it received the times 2 map, but now this becomes a short exact sequence on the E3 page, and so it's exact, so there's no homology left, and we're good. And of course this D3 is surjective onto this Z mod 2, so that all dies. Okay, excellent. So now we're off and running. And where do I want to look next? I think I want to use this D3 of y to the n. I think I jumped the gun on writing that one, because now I also have z y squared z. I have the z generated by y cubed z. I've got the z generated by y to the 4th z, right? Just using this tensor product, and so on. Okay, and this D3 of y to the n being n times y to the n minus 1z tells me that this D3 differential is now times 3. This one times 4. This one times 5. And so on as we continue. So all of these are injective, but none of them are surjective. All right, so we'll have to correct for this, much like we did in the previous spot, though somehow it's a little bit more complicated here. So let's look at this little piece. This map is injective, so I'm good for homology there, but I have a problem here. On the E3 page, if the differential out is 0, oops, that's not where it goes. That's D2, that's D3. D4 is certainly 0. There could maybe be a D5. But if D3 is 0, then I'm going to end up with Z mod 3 here. Okay, and I know that if that happens, it still needs to eventually die. Well, we just saw that it could support a D5 differential, so we'll have to see which one it turns out to be. And we'll figure that out by computing, well, let's say D3 of y squared z. Let's see if the Leibniz rule tells us anything. Okay, so the usual sort of thing happens here. Z is a cycle, right? The differential is 0 there, so I'm just going to have D3 of y squared z and then plus 0. And so this just gives me, what did D3 do to y squared? It gave me 2yz, and then I multiply by z, so I get z squared. Okay, so I have 2yz squared, and that is not in the picture. So I got to go back to the tensor product. I had this z mod 2 generated by z squared. And when I say go back to the tensor product, I mean that this whole page should be the tensor product of the cohomologies. So I'm also going to end up with a z mod 2 yz squared and a z mod 2 that looks like y squared z squared and a z mod 2 that looks like y cubed z squared. And you can see I should have made these boxes even bigger, but then it wouldn't fit on the page. Okay, so it helps to be sort of organized here and maybe have better handwriting than I do. Okay, so the point of that was that this differential y squared z is supposed to hit 2yz squared. So that's 2 here, but that's 2 in a z mod 2. So that's actually 0 because we're in a z mod 2. Okay, so it turns out this spot doesn't support a D3 differential. This differential is 0. The next differential is a D4. That's definitely 0. And so the next differential is a D5, and that's really our last chance because D6 would take us out of that first quadrant. Also notice this spot, it's not like we can hit it from something else because a D2 would come from here. A D3 would come from there, we already know about that, and then D4 we'd already be off the page. So it must be that, let's try to find a different color. That one's pretty similar, but purple. Okay, so it must be that we have a z mod 3 here to receive that D5 differential. And it has to be a z mod 3 because we know that we need this to be exact so that all the homology dies. Okay, so now that class isn't related to z, right? Z squared's in degree 6, z cubed would be in degree 9, so we could just name this something new, say A. I guess I've gotten around to the end of the alphabet. And then, as always, that's going to give me a z mod 3 here. That looks like ya. The generator here looks like y squared a, y cubed a, and so on. Okay, and I'm just getting lazy, but this, of course, keeps going. In fact, forever. Okay. Do I want to keep going? Maybe. Okay. I'm trying to decide if I want to keep going because I'm running out of space here. And so what I'm going to have to do is scroll back and forth to the next page or maybe erase some things. But let's see. Maybe I can at least fit one more in here. So let's go back to our D3 and look at this next spot. So I'm going to look here. We knew this receives a times 4 map, and this isn't even a z mod 4, so I can't hope that that kills it, but maybe that at least takes care of part of it, and then perhaps there's more. So D3 of that class, y cubed z, well, the same thing that just happened above is going to happen here. So we'll get D3 of y cubed times z plus 0. And so that's just going to be 3y squared z, but then we multiply by z again, so we get 3y squared z squared. And 3 is equal to 1 in this z mod 2. So in fact, we do have a D3 differential here, and it's surjective. Okay, but that does leave us behind some extra. right? When I look at this sequence, it's not exact because here I had a z mod 4. This only takes care of a z mod 2. I've got an extra z mod 2 hanging out. So, okay, it can't die here. Okay, I suppose I haven't argued that yet, so let's come back to the bottom here. This spot needs to be 0 because it could only receive a differential from here, here, or here. And of course goes off the page. Okay, I look at this spot and it can only receive a differential from here, 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 or here, but that's already gone by then. So that's also 0. And that gives me these zeros up here. So on. These zeros that I'm now filling in come from that the coefficients are 0. Okay, so we were just talking about this spot, that there's an extra z mod 2's worth of stuff, and it can't be hit by either of these spots. We know only only 4 z's hit there. It can't support a D2. We saw there's a D3. There could be a D4. Oh, no, those coefficients are 0. I really should have filled this all out. Okay, where were we? This can support a D3. It does. D4 would be 0. D5, well, I'd only have a z mod 2 left, and it can't map to that z mod 3. D6 is 0. D7, okay, so there must be, in yet another color, a z mod 2 here. Did I get that in the right spot? This is supposed to go, that was 3, 4, 5, 6, 7. Yes. Okay. All right. Maybe rather than sort of scrolling around and making things really confusing, let me just stop there for a moment. But I think that hopefully you start to see the kinds of games you can play. The one last thing that I wanted to do that I was hoping to get to in this example is to see that it doesn't make sense to talk about something that died earlier. So what do I mean by that? I mean this Leibniz rule game that we're playing. For example, I can't write something like D5 of, say, I don't know, y squared z. We already know what it's supposed to be, but what I'm trying to say is it's not D5 of y squared times z plus y squared D5 of z. We can't just use the Leibniz rule there because this is not a thing. Y squared has died before it gets to the E5 page. So I just wanted to go a little further to sort of caution you against running into those kinds of things. But I guess I'll just sort of caution you as an aside and say that this computation, you can keep going. So this is a good exercise to take this a little bit further. Along that line, let me give you a few more exercises. So the best way to learn to do these computations is to start playing this game. And so some good exercises are to compute, well, in the same kind of vein, let's say compute the cohomology of our rational Eilenberg-MacLane spaces. And you can do that in rational coefficients. And I hesitate to say this, but in the grand scheme of how these spectral sequence computations go, this is fairly easy. So this is much closer to that first example we did. A little bit more interesting, you can compute the cohomology, well, I'd say much more interesting, the cohomology of kz mod 2n in z mod 2 coefficients. And this starts out a little bit harder, certainly, but it is solvable, and this is maybe one of our most important examples for where we're going from here. If you get really into it and you're looking for a challenge, a fun one is to look at kz localized at 2n and compute cohomology in integral coefficients. And this gets pretty hard at some point, but in the beginning it's sort of on par with the previous computation, and I think it's a fun one. You get some other interesting stuff that doesn't show up in those first couple. Okay, maybe let me say, to get these started, one thing that you want to think about is starting with Ka1. You're going to want that to be your fiber so that your base can be connected, and so you'll want to know the cohomology here. But you do know pi 1 is A, and the Hurewicz theorem will tell you that H1 then is also A. And so you'll learn is that if you want the cohomology of Ka1, say in integral coefficients, that you'll get, oops, I did mean to write that you'll get Z in degree 0, A in degree 1. This is now cohomology, so that doesn't, I mean, it follows from what I wrote above, but it's not just repeating it, and then you'll have 0 else. Okay, so that'll give you your cohomology of your Ka1, and now you can kick off your path loop fibration with a connected base, your Ka2, and start to do these computations. Oh, and let me say, it would be good to start thinking about these computations. Absolutely do exercise 1 before we meet on Wednesday.